So welcome again, and let's talk today about the resolution of vectors and operating its scalar components. So basically, what is resolution of vectors? The opposite action of addition of vectors is called resolution. For example, if we have a vector c like this, and we have two vectors like c1 and c2, and I'm just trying to make a parallelogram here so that vector c1 is here and vector c2 is here, and you can see in the picture that for a given vector c1 and c2 are two coplanar vectors whose sum is c. That means what I'm trying to tell you, that vector c1 plus vector c2 is vector c here, and then vector c1 and vector c2 are called components of a vector c. But these are vectors, not a scalar, and this is a two-dimensional resolution involving two component vectors coplanar with the original vector. And I'm still not talking about the scalar components. So I'm just trying to resolve the fact that resolution of a vector is called the opposite action of addition of vectors. If we become more specific, or if we are not going to be more specific at this moment, and we are going to tell like this, that vector c is here, and c1 lies c2 vector, the line of action of c2 vector is this, and the line of action of c1 vector is like this. This is the line of action of vector c1, and this is the line of action of vector c2, and we have a vector c, and we just made a parallelogram here like this, though they look like they are perpendicular, but they are not if this angle is alpha and this angle is beta. So what will be the scalar components of vector c along vector c1 and vector c2? So these scalar components will be this and this along the line of action of vector c2 and vector c1, and you can find them using sine formula or cosine formula. Suppose that you want to find the scalar component of vector c along c2. So this specific component, a scalar component along c2, can be written as suppose I write this simply, and this the component of a scalar component of vector c along the line of action of vector c1 in the direction of vector c1 as b. We can use this parallelogram's credentials, and we can use either of these two triangles. We have either of these two triangles, and we can write here, if this angle is beta, this angle is also going to be beta, and if this angle is alpha, the next angle, if this angle is also alpha, and you can use either of the triangles, and you can write a upon sine beta is equal to c. I've taken this c divided by 180 minus alpha plus beta, that is c upon sine alpha plus beta, and you can get a equals C sine beta divided by sine alpha plus beta. And in the similar manner you can find B, as you can write here, B upon sine alpha equals C upon 180 minus alpha plus beta, that is sine alpha plus beta. And you can find your B as well as C sine alpha upon sine alpha plus beta. And if you have other informations, you can use cosine rule as well to find them in more specific and more direct manner, but I'm not going to use it. I'm talking about a scalar and vector components. Of course, if a vector is sum of two vectors, these two vectors are said to be the components of the original vector. But finding a scalar components means we are finding projections of vectors, projections of one vector on another, along the other, onto the other. And finding a scalar components is a purely trigonometrical work, geometrical work, and you can use sine or cosine formula. But if we become more specific, when C1 and C2 are perpendicular to each other, that means we have a vector C here, and C1 and C2 are the line of action of C1 and C2 are perpendicular to each other. We can still make a parallelogram that will become a rectangle this time, and we have more credentials available right now. If we make it x-axis, call this y-axis, and take the angle made by vector C with x-axis as theta. The scalar component of vector C can be simply written as C cos theta, and just name it Cx, that is x component of vector C, and y component simply as C sin theta, that will be the y component of vector C, written as simply as Cy. And then you can write more things using geometry, simply using geometry, nothing else. That modulus of vector C will be under root cx square plus cy square. Tan theta, you can find a tan theta here, that will be cy upon cx, and you can do many things and these are scalar components. This cx and cy are scalar components of vector C. And the advantage of using a scalar components, that we can add or subtract vectors using their components. Suppose we have two vectors A and B, and we are going to get vector A plus B or vector A minus B as simply as vector C. Then for example, A plus B, I just call it vector C. Then to find the x component of vector C, you can add x component of vector A and x component of vector B. To find the y component of vector C, you can simply add y component of vector A and y component of vector A and y component of vector B, and then you will have Cx and Cy, and you can find under root cx square plus cy square equal to modulus of vector C. And if you want to know what angle made by vector C with any of the vectors, vector A and vector B, suppose that vector C makes an angle theta with vector A, or if you want to know what angle is being made by vector C with the x-axis in particular, you can write simply as tan theta equals cy upon cx, and vice versa. But one thing should be clear here. When you use scalar components of a vector, you should have to keep in mind that components are treated as coordinates when we work with a coordinate axis and components of vectors. That means what I'm trying to tell you, that in first quadrant, the components of any vector in x component should be taken as positive, x component should be taken as positive, y component should be taken as positive if the vector lies in the first quadrant. If the vector lies in the second quadrant, its x component should be taken as negative and y component should be taken as positive. If the vector lies in the third quadrant, its both components should be taken as negative, and in the fourth quadrant, x component of the vector should be taken as positive and y component should be taken as negative. That is what we do when we use scalar components of a vector. So you must have known these things, and you have to know these things. But I want to focus. I want to focus. I want to have your attention on the different thing, on a different operation. That if we have two vectors and vector A is equal to two vectors, vectors A and vector B, and vector A is equal to vector B, then if you have vector A, if you have three components of vector A, say you are working now in three-dimensional coordinate frame, and you have all three components of vector A and vector B, and in the similar manner vector A, as we did in two-dimensional plane, vector A can be written as but leave it for now, because I forgot to introduce one more thing, that is called the unit vector basically. So we will for now we are limiting ourselves to about the components, about the resolution of a vector and components up to this point only. Let me introduce you first the concept of unit vectors. And what is a unit vector? It is sometimes convenient to express a vector C as the product of its magnitude and a vector, suppose vector A of unit magnitude and having direction corresponding to the vector C. People love to write vectors equal to its magnitude divided by its direction, multiplied by its direction, magnitude multiplied by its direction. So they write it as the product of its magnitude and a vector of unit magnitude only and having direction of the corresponding vector. And this vector A is called a unit vector, and it is usually not written like this, but it is written like a cap. A cap is placed. It's a new notation you can use for vectors having a magnitude equal to unity, and they are the unit vectors, and they have no dimensions. And that means we formulate this vector as unit vector A in the direction of C, unit vector in direction C, as simply as vector C divided by magnitude of vector C. Clearly, this development makes this vector, because this is multiplied by a scalar 1 upon modulus of vector C multiplied by vector C, and this makes them their magnitude equal to unity, and fulfills the requirement that have been set for this vector. And we can express any vector C in form like vector C is equal to modulus of vector C multiplied by unit vector in the direction of vector A. And one thing is for sure, that unit vectors that are of that the unit vectors that are of particular use are those directed along the directions of coordinate axis of a rectangular reference. Suppose we have XYZ axis like this, this is x-axis, this is y-axis, then this is z-axis, then a unit vector I is assigned along the, this is convention, unit vector I is assigned along the x-axis, unit vector j is assigned along the y-axis, and unit vector k is assigned along the z-axis. And any vector c in 3D space can now be written as x component of c multiplied by unit vector I plus y component of vector c multiplied by unit vector j, and czk in the similar manner. And what I wanted to tell you earlier, I'm now going to tell you now that if we have two vectors a and b such that vector a is equal to vector b, then we can say here that that means this thing can be written as simply as axi cap plus ayj cap plus az k cap, and that will be equal to bxi cap plus byj cap plus bz k cap. And since the unit vectors have mutually different directions, they are mutually perpendicular, so we can conclude that they are independent of each other. So we can write here as axi cap equals bxi cap, and ayj cap is equal to byj cap, and azk cap is equal to bzk cap. And it follows that ax equals bx, ay equals by, and az equals bz. Just notice one thing, that I haven't cancelled vector I with vector I. I just took their modulus. I have written their magnitude here because vector division is not possible. This is a meaningless operation, and so you use unit vectors like this. Unit vectors are basically providing the direction of a vector, and any vector can be written as vector equals its magnitude multiplied by its direction. If you know the any vector in the direction of a vector and you know its magnitude, then you can write it simply magnitude of this vector multiplied by the unit vector in the direction of this vector. And so unit vectors are basically guide. Their magnitude is constant. Their directions may or may not. I'm not going to take care of these things right now. So I'm simply introducing the concepts, and next concept is a scalar or dot product of two vectors. Scalar or dot product of two vectors. And what is this? In elementary physics, work is defined as the product of the force component in the direction of displacement times the displacement. In effect, two vectors, force and displacement, are implied to give a scalar work. So, and in other physical problems, vectors are associated in this manner so as to result in a scalar quantity. This operation is called a scalar dot product. For two vectors A and B, we simply write as A dot B, that is a scalar product. That means two vectors are going to get multiplied and give you a scalar, is defined as simply as modulus of vector A, modulus of vector B, and cos alpha, where alpha is the angle between the two vectors. Suppose we have two vectors, vector A and B, and the angle between them is alpha, then you should write like this. And you will notice immediately that the dot product may involve vectors of different dimensions. Here A can be force and B can be displacement. So they may involve vectors of different dimensional representation, and it may be positive, negative, or zero. when alpha is either less than, greater than, or equal to 90 degree, because you know cos 90 is equal to 0. And when alpha lies in the first quadrant, that is when it is less than 90 degree, the cos alpha being positive, and when alpha is between 90 and 180 degree, because the angle between two vectors cannot be greater than 180 degree. So when alpha lies in the second quadrant, and their dot product is going to be negative. And one thing you want to notice, if you want to notice, and that A dot B is equivalent to something else. Suppose that I have a vector A and this one is vector B, or at least the line of action of vector B, and this angle is alpha. Then you can simply project vector A on vector B, and projection of vector A onto the line of vector B can be simply written as A cos alpha here from the geometry. And the dot product of two vectors A dot B is the A cos alpha multiplied by B, that is magnitude of vector B, and A cos alpha is the projection of vector A onto B multiplied by modulus of vector B, and vice versa. Of course, the appropriate sign must of course be assigned positive if the projection component of vector A and vector B point in the same direction, negative otherwise, no problem at all. And you can do a lot more things with the dot product simply by introducing simply from its definition. And what can you do? To first, you have to know some properties of dot product. If you want to find a scalar product of two vectors simply written as MA and NB, where M is a scalar, A is a vector, N is also a scalar, and B is another vector. And you want to find MA dot NB, it will simply become Mn multiplied by A dot B, nothing else. And you can notice another thing, that A dot B and B dot A are not different, they are the same, because A dot B is AB cos theta and B dot A is BA cos theta, and both are same. So clearly the dot product is commutative. And if you want to consider few things, like if you try to find A dot B plus C, you will simply get A dot B plus A dot C, and that means the dot product is a distributive operation. That means the dot product is distributive. And if you want to do more things, like if you try to find out the scalar product between unit vectors, suppose you want to find the product I dot j, this will be a 0, since the angle alpha is 90 degree now, which makes cos alpha equal to 0. And on the other hand, if you try to find I dot I, that will come out simply as modulus of I cos 0, and that will be 1. So we can conclude that the dot product of equal orthogonal unit vectors for a given reference is unity. That means I dot I, j dot j, k dot k is always equal to unity. You will find it I dot a, j dot j, k dot k. These things are going to be unity. And that of unequal orthogonal unit vectors, that means I dot j, j dot k, k dot I, or any combination of this, will be always equal to 0. And if you want to express something like if you have a three-dimensional coordinate system like this, unit vector I along x-axis, unit vector j along y-axis, unit vector k along z-axis, and if you have a vector in 3D space simply as c, and suppose it makes an angle, I don't know, alpha with x-axis. How? But it did make an angle alpha, and this is, of course, as it looks, this is not equal to 180 degree. It is some angle, I don't know, because C is in a 3D space. So you can always write the x component of vector C as C dot unit vector I, because if the vector C makes an angle with x-axis, the x component of vector C will be C cos alpha, and C dot I is also C cos alpha. If the vector C makes an angle beta with y-axis, the y component of vector C is going to be C cos beta, and C cos beta is vector C dot unit vector j, and Cz in the similar manner can be dot product of vector C multiplied by unit vector k, like this. So try to gain insights on this in these things, and I can give you another aspect to think. If you try to find A dot B when A is written in component form like AXI cap plus AYJ cap plus AZK cap, and vector B as BXI cap plus BYJ cap plus BZK cap, try to multiply them, use the insights you already gained, and you will get that it will become AXBX, a product of x component of vector A and B plus product of y components of A and B plus product of z component of A and B. And if you try a manipulation like you can write A dot B equals modulus of A modulus of B cos alpha equals AX BX plus AY BY plus AZ BZ. You can also get cos alpha, that is we can use somewhere to find the angle between two vectors if the vectors are written in component, and that will become simply, after manipulation you can write them as this. But let me find you, how can you find the modulus of vector A and modulus of vector B if the vectors are given in terms of their components? You know, A dot A can be simply modulus of vector A multiplied by modulus of vector B cos 0 equals modulus of vector A square, or simply A square. So this means A square means you can write them as AX square plus AY square plus AZ square. So what you got here, that modulus of vector A is nothing but under root modulus of A dot A, and that is how you are going to find modulus of vector A and modulus of vector B by using dot product as well. And you can do one more thing, like suppose you have a vector C, because A and B are I have used many times vector A and vector B. Suppose we have a vector C, and x component of vector C can be written as C dot I cap, and y component of vector C, that C dot unit vector j, and z component of vector C by unit vector C dot unit vector k. And if vector C makes an angle alpha beta and gamma with x, y and z axis. You can write c dot I simply as c cos alpha, c dot j by c cos beta, and c dot j by c cos gamma. And if you try to find out, if you sometimes cos alpha is simply written as L, and cos beta by M, and cos gamma by N. So you can do one thing. You can write c square equals cx square plus cy square plus cz square, and that means c square L square plus c square M square plus c square N square. And this thing is c square, so you are writing here c square equals c square L square plus c square M square plus c square N square, and that gives you L square plus M square plus N square equal to 1. And this is a familiar geometrical relation, that the sum of the squares of the direction cosines, this L, M, N, are called direction cosines of a vector. And what we just got, that the sum of squares of the direction cosines of a vector is equal to unity. When the vector is, of course, in 3D, like here right now, and you just try to consult a textbook, because I'm not interested in talking vectors. I have just introduced the concepts of vectors, and I will be using them. Their use is more important, and when they are used, they provide wonderful results. So vectors, these are the basic operations, and you should consult a textbook. You can take lectures, and this lecture is not very descriptive, I see. And I'm going to introduce you next cross product, and that will be all that dot cross product and scalar triple product, their methods, and that will be all through vectors. Thank you very much.